All right, so this is great. We have two people giving one talk for the last session. So many thanks to Nathan Brady and Anindya Sengupta, who are going to tell us about Tadpole and Moduli in Type 2B on the, I'm not going to keep reading it, you can talk.
Thank you very much to the organizers for giving us this opportunity to talk. And we are going to talk about Tadpole and Moduli in Type 2B string theory compactifications using the 1 to the 9 Landau-Ginzburg orbifold. So this is some work that we have done with our advisor, Catherine Becker. So let's go right into it. So I'll begin by setting up notation and describing the model. And towards the end of the talk, in the second half, Nathan will tell you the new results that we have found. Okay, so fluxes in string theory compactifications are important for many different reasons. The particular aspect of flux compactifications of type 2B that we are interested in is stabilizing moduli. So in DGKT back in 2005, it was shown that in massive type 2A, on a rigid Calabi-Yau, which has no complex structure moduli, fluxes and orientifold 6 planes, they can stabilize all of the moduli. So this sort of motivated Becker, Baffa, and Walcher back in 2006 to study the mirror dual setup, where you take type 2B on the mirror dual Calabi-Yau, which has no Kähler structure moduli. So they are non-geometric, because if you look at type 2B supergravity compactifications in the geometric setting, the size of the internal manifold will always show up as a Kähler structure modulus. So since we don't have any in this setup, we can safely say that the internal manifold is non-geometric in some way. So, but in string theory, we have ways of producing these things. Essentially, all you have to do is to produce an internal superconformal field theory with the appropriate central charge, which is equals 9. And these models are good because since you have no Kähler moduli, you don't have to stabilize them. And all of the complex structure moduli are putatively stabilized by the flux-induced superpotential. At least that was the claim that was made by the authors of this paper. But more recently, Catherine with her collaborators in 2022, they looked at all of the solutions that were presented in this paper, and they found out that all these solutions, all the flux vacua, they have a large number of moduli which are massless. So essentially back in 2006, they were so confident that the flux-induced superpotential will stabilize the moduli, they didn't even bother looking at the masses of the fields. But closer look at those solutions revealed, and this paper also presented more new solutions, and in all of those solutions there are a large number of moduli that are massless. Okay, so what do we do? Do we stop looking at the solutions altogether? No, because the two really nice properties that they have, the fact that there are no Kähler moduli, and also the non-renormalization theorem of the flux-induced superpotential, these two properties make these models still very attractive. So what one can do is to find more systematic search for solutions and try to find solutions where you can increasingly stabilize more and more moduli. The reason why this was not done back in 2005 is because the lattice of supersymmetric Dirac quantized flux backgrounds in these non-geometric Landau-Ginzburg models, they have a really large rank. So a brute force search for short vectors, by short we mean fluxes which do satisfy the Tadpole cancellation condition, it is quite expensive. So the work that we have done with Catherine, in that we essentially start systematizing the search for solutions in these models. Okay, so let me first give you the basic ideas. So we essentially write down string theory where C equals 15, where M4 is the non-compact space-time directions, and M is the internal SCFT where C equals 9. Now, an N equals to Landau-Ginzburg QFT of chiral superfields is usually given by this kind of an action, where this W is the world sheet superpotential, and this K is the Kähler potential. So there should be a comma right here that's missing. So it's believed that it flows in the infrared to a CFT provided K is chosen suitably. The world sheet superpotential W only receives wave function renormalization. So if we choose the superpotential to be quasi-homogeneous polynomial, this can be absorbed in W as an overall scaling. For one chiral superfield with a superpotential of this form, phi to the K plus 2, where K is some integer, central charge of the infrared fixed point is given by this, and it is precisely the central charge for the kth minimal model of the N equals to SCFT. So if you take, instead of one chiral superfield, if you take n of these and tensor them together, you get the total central charge to be 3 times nk over k plus 2, which equals 9 if you choose k and 9 of from this set. So 1 for k and 9 for n, or 2 and 6, 3 and 5, excuse me. Or 6 and 4. So this model goes by the name of 1 to the 9. This goes by the name 2 to the 6, 3 to the 5, and 6 to the 4. So for specificity, we'll focus on the first model, 1 to the 9, and we'll take an orbifold of this guy. So in 1 to the 9 mod Z3, we take the k equals 1 minimal model, and the world sheet superpotential is given by the sum of the individual building blocks. And there is a diagonal Z3 symmetry in it, where each phi goes to omega times phi, where omega is a cube root of unity. So how do you count how many complex structure moduli and Kähler moduli this model has? Well, essentially, since the internal manifold here is non-geometric, you cannot simply count how many co-cycles or cycles you have. So you have to give a CFT description. So it can be shown that the chiral and antichiral superfields in these models, they have a ring structure, and the CC chiral ring given by this. So this is the ring produced by the 9 fields that you have. The ring operations are plus and the operator product, modulo the partials of the superpotential going to 0, which is phi 1 square to phi 9 square. They count the H21n elements. So you have 84 of those. You can show that there are 84 different ones in the 1 to the 9 model. And there are no Kähler moduli because there are no non-trivial AC primaries in this model, or even when you Z3 orbifold it. So H11n is equal to 0 as well. So now, because we want n equals 1 supersymmetry in 4D, we take an orientifold. So the orientifold action is given by tracing the parity, world sheet parity, B-type parity operator with the following holomorphic involution of the internal space, where phi 1 and phi 2 are flipped, and an overall minus sign multiplies the entire thing. And then one can compute how many of these complex structure deformations survive under the orientifold action. And you can see that there are exactly 63 monomials of the ring, which are of the form phi 1, phi I, phi j, phi k, I and j and k are not equal. And you count there are 63 different combinations of this kind. Okay. So now we have to also give a description of branes and fluxes in this non-geometric setting. Because these are not manifolds, again, you have to precisely define from the CFT perspective what do you mean by supersymmetric cycles. And it's best to look at supersymmetric cycles in this setting by looking at A and B branes and distinguishing them by the boundary conditions of the super current operators G plus minus. So you can either impose this boundary condition or that one, this is the A type and this is the B type. So in the phi space, A branes, so now we are talking about one of the building block minimal models. You can show that the A branes in the phi space are pre-images of the wall sheet superpotential having a constant phase, which by using some R rotation you can fix to be the positive real axis. So each building block minimal model essentially comes with these three non-compact cycles, which we call V0, V1 and V2. They are clearly related by this equation that V1 plus V0 plus V2 is 0. Now, a cohomology basis of the space of A-brane charges are spanned by the RR ground states L. This is again for one building block minimal model, L goes from 1 to 2, and they are represented in the chiral ring in this fashion. So essentially you only have 1 and 5, so there are 2 elements that generate the entire ring. The correspondence is that for each RR ground state, you essentially assign phi to the L minus 1, and with some normalization factor that we choose for convenience, and I'm suppressing it in here. So how do you calculate the Ramon-Ramon charges of the A branes? Essentially you compute a one point disk amplitude like this, overlap, and essentially it amounts to computing a simple integral of this kind. And when you have 9 of these models tensor together, your RR ground states would be a tensor product of 9 states of this kind, and then you have to see how many of those survive this Z3 orbifolding and so on. And without going into more details, I'll just simply state the result that the HPQM with P plus Q is equal to 3 is given by ground states of this kind with this condition imposed, where the sum of the Li's has to be 0 mod 3. So you can either get 3 or 6 or 5, 3 or 6 or 9 or 12 or all the way up to 18, I think. Yes. You get 9, 12, 15 and 18. Hold on. I'm missing something. Yeah, if you get if you choose all the L's as 1, you get 9, and then if you take all the L's as 2, you get 18 essentially. Yeah. So those are your options, and the Hodge degrees in terms of the values of PQs, they can be identified by looking at the U1 charges of the internal n equals 2 SCFT algebra, and these are the classifications of the PQ forms. So the three form fluxes in the NSNS and the Ramon-Ramon sector are supported on A branes, and we complexify this in this fashion, and then the tau is the axial dilaton, and for supersymmetric Minkowski vacua, the flux has to be H in H21N. So we only look at, for this particular part of the project, we only looked at Minkowski solutions, but there also exist ADS vacua in this model. So this is one of the conditions that we impose, that the sum of the L's has to be 12. So the orbifold of the tensor also identifies brane states by summing over orbits. So essentially you can define 3 cycles, which are tensoring the 3 cycles from the building block minimal model, but the ones that survive the orientifold action. So there is a basis of 128 3 cycles that you can define. Yes?
Sorry, I have a very dumb confusion. So A brane doesn't have to distribute it in that open like B, and what you mean by from A brane, right?
Yes. So the A, A cycles, the cycles we are calling A branes, essentially. Yeah. So all right. So there are 128 different 3 cycles, independent 3 cycles in this model, and there's a basis, there's a construction of it. We don't go into the details, but on each element of the basis you impose the Dirac quantization condition, which goes like this, and then where n and m are integers, of course. And the B-branes, usually you use the method of matrix factorization to construct the B-branes. And they are useful because they can support orientifold planes and other sources. And again, skipping details, we can show that the orientifold that we are considering, it has a Q3, a D3 brane charge of 12 when you use the matrix factorization technology. So the Tadpole cancellation condition for the models we are considering looks like this. N flux plus number of mobile B branes that you can have, D3 branes, has to be 12, where the flux Tadpole is given by this formula. Okay. So there are some crucial properties of the flux Tadpole that are useful in analyzing solutions. So take an arbitrary flux, which is some complex linear combination of the 63 different fluxes that you can turn on. The B's are complex numbers, and impose the Dirac quantization condition on a basis of 3 cycles. So essentially, the real and the imaginary parts of B, they get related to 126 integer variables. We call them flux quantum numbers and denote them by Y. And when you calculate the flux Tadpole, the formula for which is which was given in the previous slide, you get this expression, where now we set the value for the axiodilaton equals to omega. So this is a order 1 string coupling. When you do this, you get 81 sum over bi squared, right? So we already know these bi's are related somehow in a linear way to these 126 integers. So when you expand this out, when you replace the variables, you find that the flux Tadpole is equal to a homogeneous quadratic in 126 integer variables, where all the coefficients are integers. So that essentially tells you that the values of the flux Tadpole are integer. And not only that, if you take one of the bi's, assume that you only had one omega, one possible flux. For that, if you calculate 81 bi squared and do the same exercise again, replace bi by what it looks like in terms of yi and yj, you get the same behavior. You get a homogeneous quadratic with integer coefficients. So what that means is that if you really do turn on a flux, it must contribute at least 1 to the flux Tadpole. So to ensure the fact that we want to satisfy the Tadpole cancellation condition, in flux has to be smaller than or equal to 12, it is sufficient to restrict to up to 12, what we call 12 omega solutions, in the sense that you need not turn on more than 12 different fluxes. So already in BBVW and BGWW, so this is the 2005 paper and this is the 2022 paper, solutions with smaller than equals 12 flux Tadpole were found. The minimum value of the flux Tadpole among those solutions is 8. So there are 2 questions that we ask in this project. One is there a flux background for which n flux is smaller than 8? And the second question is, how can we systematize to find all solutions with this bound? And in order to check how many moduli are stabilized, we need to know something about the flux induced superpotential. Now in the traditional geometric setting is given by this GVW formula, where W is G wedge omega integrated over the internal manifold. Now this continues to hold true for I think I wrote this wrong, not 2B on 3-folds, I wanted to write 2B on the Landau-Ginzburg orbifold. Now this flux induced superpotential does not receive any perturbative or non-perturbative corrections. So there are arguments by these authors that this formula does not receive any corrections in all orders of perturbation theory, both alpha prime and string coupling. Now in BBVW back in 2005, they also proved that this continues to hold true for non-perturbative corrections as well, because all the relevant instantons that could correct it, they do not exist. So this tree-level formula for the superpotential is exact. So if we want to see how many moduli are stabilized, we can take this, the tree-level superpotential and calculate the rank of the mass matrix with it. And the other interesting feature that this has is that because we are looking at Minkowski solutions, we don't have, so essentially the condition is that W is 0, and therefore the supersymmetry condition goes to this. And because of this, we can show that the rank of the Hessian of the superpotential is exactly equal to the rank of the mass matrix. So all we have to do is to calculate the Hessian of this guy and calculate its rank. So in order to tell you all the properties of the solutions that we find, this property is going to be really important. Okay. So now Nathan will tell you a systematic explorations of the solutions that we have found. Here you go. Thank you. Hello. Oh, yeah. Can you hear me? I will assume so. Excellent. All right. Thank you, Anindya. So, like you said, I get to tell you all about the results that we found for this particular model. And there are some conditions I want to sort of recap. We have the tadpole cancellation condition. Make sure I understand. Which was stated before in the previous slides. We're looking for a physical, so when that is satisfied, we call it a physical solution. It's sufficient to restrict our search to fluxes which are below 12, which comes from that tadpole cancellation condition. Next, so restricting our search to look at fluxes which can get progressively larger. We're turning on more complex structure moduli, or more fluxes, I should say. So our search is an order by order in number of omegas turned on. So searching through all possible 12 omega configurations is obviously computationally difficult, but we present this another direction of going about it by eliminating order by order tadpoles that can't don't saturate the minimum tadpole value. So we're going to find a minimum value for this particular model. So as a crude lower bound and for the tadpole flux contribution, for the set of n omega flux backgrounds, now we're finding the best lower bound. And we find that we give a complete set for omegas up to 4, and what those lower tadpole values are. So, okay. So for the 1, 2, and 3 omega solutions, on the left here, the form of the flux appropriately normalized with the correct coefficient there for quantization. We find the minimum tadpole value for 1 omega is 27, and this is just the enumerated list of complex structure moduli that we established beforehand. There's a typo here. There should be, oh wait, that's later on here. So we find they can stabilize 16 massive scalars, or 22, depending on your choice of index, in this enumerated list. That's the rank of the mass matrix, as Anindya mentioned before. Here, like I said, this was in our enumerated list. These are the oriented full directions. There's a typo here. There should be actually 56.
But we find that its minimum tadpole value is twice as large as the one where we were not in the orientable direction, and it also stabilizes 22 scalars. In the 2 omega case, we find the minimum tadpole is 18, and they can stabilize 16, 24, or 26 for this set of index enumerated complex structure moduli. And in this set, it's 28 or 32. Next 3 omegas, we have 2 choices here. We find that its minimum contribution to the flux tadpole is 27, and it stabilizes anywhere from 16 to 46 in this set. Yeah. Okay. Next is going to be, oh, did I skip it? There we go. Next is our first situation where we actually satisfy where we find that the tadpole contribution is actually satisfied. So we find the minimum flux tadpole is 12, and our first example with a physical bound, we can see that we'll have this form, which you can check explicitly and by using the equation for the flux tadpole, 81 times the sum of the coefficients squared. You can check and see, yes, you reproduce tadpole value 12. This was this also, if you include phases, you can get you can express this as a family of solutions. We found exhaustively these, and the phases, the properties of this, you can check that if this is properly quantized, then this one should also be properly quantized. The quantization condition in this situation follows this pattern, where it's the sum and difference of the appropriate phases here, and this is your quantization condition. We find that this is properly quantized if and only if this relationship of the coefficients A, B, C, and D, the sum and difference of those, modulo 3 is equal to 0. Okay. So this is an exhaustive list of that of the minimum tadpole for the 4 omega solutions, and here alpha, beta, gamma were the associated values there, the enumerated list. So we find this set stabilizes scalars from 12, 22, and 26. Okay, moving on, out of time. So the shortest vector problem. So we actually answer this question that Anindya proposed, is are there any tadpole fluxes that are smaller than 8? And we found exhaustively that that answer is no. 8 is our minimum tadpole for this model. We do this by ruling out, as I said before, in our procedure, and so I'm going to describe the procedure now, is to rule out these by looking for specific tadpole flux values that are less than. So we turn on order by order, and this is allowed because the minimum value for a tadpole, the minimum contribution that they have is 1. So turning on 1 should at least contribute 1 to the tadpole cancellation, the tadpole flux. Okay. So choose T complex B's. So 2T, set of 2T equations, non-zero, and set the remaining to 0. So we have a set of 114 real linear equations in integer flux quanta, which Anindya mentioned, we described it as Y. So this set of non-zero coefficients gives us a reduced expression for that tadpole flux. And so we express it like this, where Qij is some symmetric positive definite matrix. That's what I meant. So where these CIs are arbitrary integer valued, form a integer value vector. So So now the question becomes, is this less than or equal to t for some choice of integer ci? And remember, we're setting t equals 7 in this problem. So this is computationally difficult. This can be computationally difficult in quadratic Diophantine equation. So we need some way of improving this timing. And so we actually managed to take a computation that might have taken a month to do in maybe a couple days, using parallelization techniques as well. So we define the level set. So what we're doing, now I'm going to describe this algorithm, which helped us do that. So we define a level set in R2T, which is this. And points that lie outside of this ellipsoid will have guaranteed values that are larger than our t-bound. So are there integer lattice points on LT or in its interior is the question that we ask. So we call this procedure the eigensieve method and an algorithm. And it's really just a combination of enumeration and sieving techniques. So using the eigenvalues of our symmetric coefficient matrix Q, the eigenvalues, the two t eigenvalues, which are positive and in increasing order like that, and the normalized eigenvectors, we can actually do an exhaustive search, and as opposed to an approximate technique. So we carve out a finite region in integer space using the smallest eigenvalue of that coefficient matrix. So lattice points in this region, which satisfy the magnitude of the point dotted with the corresponding eigenvector, is larger than the square root of the fixed flux tadpole value, which we set to 7, divided by the associated eigenvalue of that eigenvector. So if a point satisfies this relationship, we sieve it off. So we explicitly, so this allows us to go through a set of points, millions of points, and check this condition, and which improves calculation time significantly. So all lie outside of this, and they are sieved off. Explicit evaluation of those that remain in this reduced flux, we actually calculate this value now. Okay. So let me summarize what we did. So we initiated a systematic search for solutions with the lowest value of n flux, and we organized them by the number of flux of omegas that are turned on, order by order, and perform an exhaustive search up to 7 omegas turned on. That's what I want to say. So this is similar to this is the shortest vector problem, which is NPR, but that's unimportant. So for the lattice of supersymmetric flux vacua in this, we find that it is the minimum definitively is 8. A large class of 8 omega solutions were found, but I should mention that this is not an exhaustive list. It is, yes, it is not an exhaustive list. And I think I must have skipped over the 8 omegas, didn't I? But, yeah, yes I did. So the punchline was the 8 omegas. So we find T-min is the minimum of this. It stabilizes 14 massive scalars. The quantization condition is this, which we picked up from the 4 omegas. This gives us a set of 8 omega solutions, but it is, like I said, not exhaustive. Okay. My butterfingers. Sorry about that. Okay, so wrapping it up. Sorry about that. So all solutions that were found have a number of massive moduli below the tadpole conjecture bound, so there's no discrepancy in that. Next steps are to push this search exhaustively, hopefully to 12 omegas, and moving away, this would likely require us to move away from the symbolic computation of Mathematica. And finally, we aim to extend all our analyses to those other Gepner models that Anindya mentioned, the 2 to the 6 and so on. 2 to the, yeah. So, thank you.
Thank you, Nathan. Thank you, Anindya. That's great. We're a little late, but a couple of quick questions. 1 or 2 quick questions. Maria.
So if I understood correctly, you need to turn on more cycles, fluxes on more cycles to lower the tadpole, which is counterintuitive.
It is, yes. So this is like the symmetry of the lattice of the supersymmetric fluxes. We don't think that we quite understand it, what's happening. So if you turn on only 1 omega, the minimum tadpole turns out to be 27. You cannot do better. But if you turn on 4, you get 12. If you turn on 8, you get 8. So we don't really know how. And the other thing is like the tadpole minimizing flux backgrounds. Those are weird in the sense that each turned on omega or flux is contributing equally. So all the solutions we have, they have this property and we don't understand why. It could have been that one guy contributes 1, the other gives you 2 and things like that, but that doesn't happen.
Andre.
I was just wondering how large your search space actually is. I mean, if you did a 63 omega case, how large would that be, for example?
Okay, so I can give you a rough idea. So it depends on what the.
I mean, I was wondering 10 to the what?
Yeah, it depends on the value of the lowest eigenvalue that we have of the coefficient matrix.
Yeah.
So if you calculate, so say you are trying to see if there are 63 omega solutions with tadpole value of 63, let's say, right? So you have to calculate square root of 63 divided by the smallest eigenvalue. The smallest eigenvalue essentially goes to 10 to the minus 5 or 6 or something like that. So it's a huge, even though the region is finite, it's
10 to the what now? I didn't follow that.
10 to the minus 6 or 7 or something like that.
Now, how many possibilities? It would be 10 to the plus.
So that's for each direction in this lattice.
Yeah.
You have to go that far out, and then you have 126 different directions to go.
Okay.
So the finite region that you carve out, that is huge. I mean, with 7 omega solutions, we went out, the finite region we carved out, it had about 100 million or so lattice points to begin with. But then by sealing off, we brought it down to about a few thousand.
So systematic search at some point breaks down, and then you have to use heuristic search methods. So did you try any of that?
No, we only have to go all the way up to 12 omegas, not beyond. So for that, even I think the search is still very expensive. We don't have the necessary computation power. So what we are trying to do right now is to not do any symbolic computation at all and make it completely numerical and see if we can still do exhaustive searches. Because the symbolic computation is essentially what is the bottleneck in this entire search.
Okay. One more question. Yeah. This is already.
Thanks. Thanks for the nice talk. You said that in all the solutions you found there are massless moduli left. Did I understand right?
Yes, that's right. So we have 64 moduli in this model, 63 complex structure moduli and the axial diagram. So when we calculate the rank of the mass matrix, it's a 64 cross 64, and then the best we could do is stabilize about 46 moduli, but the tadpole value is quite high.
Did you check if this is just a quadratic order? So is there a modular space,
or are
they lifted?
Rank of the mass matrix, right? So you are only calculating the Hessian of the superpotential. So you could actually, in principle, calculate higher order terms. So that's another aspect in which we are looking into at the moment.
Okay, thanks.
Oh, go on, one more, just mind you.
Just relatedly, these solutions are at W equals to 0 or W not non-zero?
These are all Minkowski vacua, so W is equal to 0.
Right, and I think that actually also explains the presence of non-stabilized moduli.
There also exists ADS vacua in these models, but we didn't look at them explicitly.
You're eating into your coffee break, but one more, I'm happy to It's good to discuss.
It's more than a question, this is a comment. It's just, this reminded me of some work done some years ago on orbifold, toroidal orientifold, set n and set n times set m. It was similar to this, and this reminded me because I think this 1 to the 9 model is related to some Z3 times Z3 orbifold.
Yeah, it's
so probably it can be put in the same language of these models that were considered before. I'm not sure if the Z3 times Z3 was considered, but ZNs were considered and Z2 times Z2 were considered.
Right, so the 1 to the 9 mod Z3 is like before your orientifold, it is dual to a T6 modded by Z3 cross Z3, almost like DGKT, but the Z3 is here, not exactly the same as the one that DGKT considered. But these are mirror duals before you turn on the fluxes.
Okay, let's thank Nathan and Anindya again. Thank you.